Hello everyone, today we're talking about Flexible Ethernet, or FlexE for short. First, we'll look at the background of FlexE. The IEEE 802.3 standard emerged in 1982, marking the rise of Ethernet technology. Since then, the Ethernet rate has been increasing in multiples of 10. For example, 10 megabits per second, 100 megabits per second, and 1000 megabits per second. In recent years, interface rates such as 25 gigabits per second, 40 gigabits per second, and 50 gigabits per second have also emerged with the development of 5G services. Even if interface rates continue to develop rapidly, there are still some limitations. First, as 5G services develop and the application scenarios diversify, the standard-compliant Ethernet interfaces cannot meet service requirements. Second, the Ethernet interface capability of an IP device interconnected with an optical transmission device does not match that of optical transmission device. The optical transmission device supports 10 gigabits per second, 40 gigabits per second, and 100 gigabits per second interfaces, but not 25 gigabits per second or 50 gigabits per second interfaces. Third, high-speed optical modules are expensive. For example, a 400G optical modules costs much more than 100G optical modules do. To address such limitations, the Optical Interconnection Forum proposed FlexE technology for the first time in 2016. It aims to flexibly allocate bandwidth based on actual service requirements, thereby eliminating bandwidth restrictions imposed on interfaces by IEEE 802.3. It also aims to reduce costs. For example, a router is interconnected with an optical transmission device, and the different services involve different traffic volumes. This is like a scenarios where goods are transported. The capacity of the truck is fixed, but the size of goods is different. We need to consider what type of truck to use and what kind of paths to take during packing. Assume that there are only 40G, 100G, and 150G, and 200G packing boxes and corresponding trucks. If the size of goods is 50G, 100G packing box and the corresponding truck must be used because there is no 50G packing box or truck. As such, wastage occurs. FlexE takes a different approach by splitting all goods, packing them according to the standardized size, and then assembling them at the pier end. This significantly reduces transportation costs and eliminates the problem of selecting appropriately sized trucks. First, let's look at the core concepts of FlexE. FlexE shim, FlexE group, and FlexE client. A FlexE shim is similar to a standard packing box. A FlexE group is similar to a transportation channel. A FlexE client is similar to a truck that is visible to customers. These concepts might be unclear at present, but we'll explain them in detail based on devices' interfaces. Now that we have a basic understanding of FlexE, we'll briefly introduce the FlexE system architecture. FlexE is configured on physical interfaces. Multiple physical interfaces can add it to the same FlexE group. A FlexE group can be divided into multiple FlexE interfaces based on different bandwidths. These FlexE interfaces are called FlexE clients. Before we introduce how FlexE is implemented, let's review the concepts of FlexE again. FlexE client corresponds to an externally observed user interface that functions in the same way as traditional service interfaces on existing IP or Internet networks. It is a logical interface. FlexE group corresponds to a physical interface on a network. FlexE shim functions as a logical layer inserted between the MAC and the PHY layers and is core function of FlexE. It decouples the MAC layer from the PHY layer so that each FlexE client corresponds to a MAC address. Each physical interface in a FlexE group can be divided into multiple data transport channels, which are called time slots. An original data flow is also divided into data blocks, which can be distributed among multiple time slots in the FlexE group through the FlexE stream. The architecture of FlexE provides three major functions: bounding, channelization, and subrating. Bounding is like a situation where a lane is wide enough only for small vehicles to pass through. So we bound two lanes to allow large vehicles to pass through. FlexE bounding can bound multiple physical interfaces to provide ultra-high bandwidth. In addition, data flows can be evenly distributed to all physical interfaces through time slot-based scheduling, achieving 100% bandwidth utilization. In addition, we can use the existing interface rates to achieve our desired rates without waiting for new interface standards. As such, bounding is more cost-effective. Channelization is like a situation where dedicated lanes are planned for different types of vehicles to prevent large and small vehicles from preempting lanes. FlexE channelization allows data flows with multiple low rates to share one or more physical interfaces. For example, a 100G physical interface carries 4 channels of data flows: one 50G channel, one 30G channel, and 2 10G channels. In standard Ethernet, all services share interfaces, whereas in FlexE, channelization provides physical layer service isolation between different FlexE clients at the interface level and provides different services LAS. EMBB, URLLC, and MMTC services on a 5G network can be carried on the same IP network through slicing. Subrating is like a situation where ultra-wide lanes allow only small vehicles to pass through, and all small vehicles can run on different lanes for load balancing. FlexE subrating allows data flows with a single load rate to share one or more physical interfaces. For example, 100G physical interface carries only 50G data flows. Subrating can be considered a subset of channelization. Based on these three functions, FlexE implements on-demand bandwidth allocation and isolation, and can be used on IP networks to implement ultra-high bandwidth interfaces, 5G network slicing, and interconnection with optical transmission devices. That concludes our introduction to FlexE function. So, what are the advantages of FlexE? More even load balancing. Compared with traditional Ethernet, FlexE can implement bit-level bonding to solve the problem of traffic being unevenly hashed in per flow or per packet load balancing on trunk interfaces. Isolated services. Each FlexE interface has independent MAC address, and forwarding between different FlexE interfaces can be completely isolated. Smooth upgrade. The network can be smoothly expanded to facilitate the quick deployment of new services without changing the network structure. Minimal cost. One network can be used for multiple purposes, maximizing network values and minimizing network adjustment costs. That's all for today. Thank you for watching.